All right, so highlights from practice test 1. Okay, this is the first problem that we haven't really gone over how to do this type of problem, but it's pretty simple once you understand what it's asking for. So for example, I'm gonna give you a molecule here, and then I'm gonna ask you all about the molecule. And the way that you'll know what I'm talking about or where I'm talking about is because I'll have the C1, C2, C3, C4, and C5. So that's just referring to which carbon I'm talking about here. So first up, we're going to talk about this carbon here, and we need to figure out the shape for it. Now, I like to also put AXE in here because you kind of need to figure out the AXE before you figure out the shape, all right? So let's do that first. So if this carbon in the center is our A, this hydrogen, and this carbon are all directly connected to that C, right? That carbon there. There's a connection right here, here, and then we have a double bond here. Okay, so that means this is an X, X, X. So this is AX3, and the shape should be trigonal planar. All right, and we know trigonal planar is 120 degrees. Now the next thing we have to do is the sigma versus pi. So let me change the color. And remember, if it's a single bond, it's going to be sigma. So these are both sigma. And then if it's a double bond, one of them is sigma and one of them is pi. So for all of this, we're going to do 1, 2, 3 sigmas, and then there's only one pi bond there. All right, and the last thing we have is the hybridization. And if you remember, we had options of sp, sp2, and sp3. And they are, sp was linear, sp2 is trigonal planar, and then sp3 is going to be our tetrahedral. So for this one, our hybridization would be sp and 2. All right, and that has to do with the amount of atoms bonded onto it. So there's 3 things bonded on there, so it's going to be sp2. Okay, any questions with what we did for that first row? Now the next thing on here, the next one, you'll see that some of them are very similar. Like the next one is actually probably going to be the exact same thing. So let's check it out. Actually, you know what I'm going to do? I'm going to erase all of this to make it more clear. Okay, so now we have our new A, and it's going to have this carbon, and this hydrogen. Okay, so it's A, X, X, X. So it's the same thing, AX3. As soon as you see that it's AX3, also, everything else is going to be the same. So we'll have trigonal planar. The angle is also going to be 120. The sigma, we can count them up. We have 1 sigma here with a double bond, 1 here, 1 here, so there's still 3. The double bond, the other one is going to be a pi. And then it's still planar, so it's going to be sp2. Okay, so it's very similar to C1. Now the next one's going to be a little bit different, so let's change it up, change the color. And so for this one we have that carbon and this carbon. So all of this is just 2 carbons connected to a central atom, right? So here's our A, here's our X, here's our X. There's no unpaired electrons around there, right? So there's no E's or anything, right? So this is just AX2. And so AX2 we know is tri-atomic linear. We know that the angle for that is 180 degrees. And then the sigma is in the pi's. Well, we already know that this one was sigma, because we did that a second ago. And then here, the middle one is going to be our sigma. And then we have a pi on the bottom and a pi on the top. So it's going to be 2 sigmas, 2 pi's, all right? And because it's linear, it's just going to be SP for the hybridization. Okay, C4 and C5. C4 is going to be the exact same as C3, right? Because C4, if this is our A, we change the color. Here is one of our X's, and here's the other X. So it's also going to be all the same thing. So we have AX2, triatomic linear, (180 degrees), 2 sigma, 2 pi, and it's also SP because it's linear. All right, and then the last one we have on here is our C5. And with this one, we have 1 carbon connected to 3 hydrogens, so these are the X's. We have another carbon over here, that's another X, so this is AX4. And that's going to give us the tetrahedral shape. All right, and everything that we know from tetrahedral. So we know it's 109.5. Sigma, it's all sigma, right? They're all single bonds, so there's 4 sigma, 0 pi, and it's sp3. And so that's how you'd fill in this chart. It's basically asking you the same information from all the other parts where, you know, you're doing the angles, the AXE, all that kind of stuff. The only new thing here is it's asking about sigma, pi, and hybridization in a chart form, okay? Okay, does anybody have any questions with that? No? All right, cool. All right, so if this shows up on the test, that's kind of what you would do for it. Now, another kind of question that they could ask is they could give you something like this and then say, all right, draw an isomer of it. Now, there's a couple things you want to make sure you do and don't do, all right? You don't want to just flip it. Because if you flip it, it's still the same molecule, it's just flipped. So what I recommend you do is if you see something like this and there's a triple bond in there, maybe get rid of the triple bond, because no matter what you do, if there's no triple bond, it's not going to be the same molecule. It means it's going to be an isomer. The other thing that you could do is you could move some of the bonds around. Now again, you just want to be careful because you just don't want to end up with, you know, a tetrahedral on carbon 5 or carbon 1, and then on the opposite, you don't want to have this kind of planar shape there, because again, that would be the same as just kind of flipping it. So what I recommend you do for figuring out if it's an isomer would be to take that triple bond and be like, okay, I'm not going to do any triple bonds. Now remember, it's an isomer, so you have to keep the same number of carbons. So we have 5 carbons and the same number of hydrogens. 1, 2, 3, 4, 5, 6. Okay, so you want to make sure that it has the same number of carbons and hydrogens. So let's do this. Let's figure this out, right? So I'm going to put a carbon, and then I'll do all the carbons, right? And they're all going to at least have a single bond. And then if I don't want to have any triple bonds, I have to figure out a way to make that work. So right now I have a double bond and 1 triple bond. So let's try to use the same number of pi bonds. So for example, I have 1 here and then 2 here. So it's a total of 3 pi bonds, right? So I'm going to try to put 3 pi bonds in here. So maybe I'll put 1 here. I have to use 3, right? Maybe I'll put 1 here and then maybe 1 over here. All right? But I have to make sure that I only put 8 electrons around each carbon, right? So this carbon, the first one, 2 of its dots are used up here. So that means it only has 2 more dots. All right? Here, 3 of them are used in bonds, so it only has 1. This one has 3. So it has 1 more. This one doesn't have any, right? Because it has 1, 2, 3, 4 things already connected to it, or 8 electrons. And then this last one has 2 here, so it still has 2 there as well. Now, hopefully when we do this, hopefully all the dots work out, meaning that we have 6 dots because we only have 6 hydrogens. And if we count them up, we have 1, 2, so that's good, 3, 4, 5, 6. So in this case, it would work out as making it an isomer. And it's definitely not the same as what we started with because, like I said, there's no triple bond. There's no triple bonds in there now. There's just a few double bonds, all right? So that's kind of one way you could do it. You can, keep track of the carbons, the hydrogens, and the pi bonds. There's 3 pi bonds in both of them. That kind of works things out, all right? Now, if you try to make less double bonds, you would need more hydrogens, right? And that wouldn't work out either. So that's kind of one way you could do it. You can also just kind of like play around with it and just move things around and see if it works. Just remember that carbon needs to have 4 electrons around it, or a total of 8 once all the bonding is done, all right? Okay, any questions with that?